In this video we're going to look at how to convert a data file that has been exported from Avantage as a .avg ASCII file that contains a set of images. The images within this data file are the equivalent of the data set we see here. That is to say that the images are acquired at a sequence of binding energies. So the file contains both spatial information in terms of X and Y, and then for each one of these images there is a data bin in terms of energy. So for a specific pixel we have a spectrum. If we gather information from a given pixel position within an image and then at all the different energies we produce a spectrum of intensities that are the intensities at each one of these pixels, then we end up with a spectrum that we can analyze as we would do if we just simply acquired a spectrum. This particular data set contains tantalum oxide with some scratches that are exposing tantalum metal. So it's equivalent to this type of arrangement where we've got an oxide peak and a metallic peak. And by considering a stack of images as a set of spectra at pixels, then we're able to analyze the data in exactly the same way we would do for spectroscopy data and produce spatially resolved chemical state information. So to convert this data set, what we need to do is enter a file name. So tantalum to oxygen 5, we'll call these maps, dot, and then I need to enter ITH. This is the conversion filter that will cause the AVG files within a directory to be processed as if they are images. And so rather than looking for spectra in these files, the image format is used, and when we press open the directory search for every AVG file, and it must be in the same image format. The data will be processed, entered into a VAMAS file that will then be opened in CasaXPS. Once the data have been processed, a VAMAS file is created, as we can see here, and then that VAMAS file is opened and we see the images, and the experimental variable will be the energy for each image. So if we step down this list here, we're looking at the images that are formed at different binding energies. So we can see the oxide and then the metallic tantalum. Once the data set is available to us as a VAMAS file, we can then process this dataset using options on the image processing dialog window. And these options include principal component analysis, or color scales, or a range of different options for marking up and extracting information from these images. Now in the first instance, we should first of all demonstrate that this dataset contains the type of signal to noise that would be perfectly acceptable for any type of spectroscopy analysis. And we can do that by simply summing all of these images into data bins corresponding to a single spectrum. So there are a set of energies, one for each image, and if we just treat each image as if it is a detector and sum all the intensity from that image into a single bin, then we end up with a spectrum. And this spectrum shows you that the signal to noise is very good, and also that you can see there's the metallic form of tantalum and there's the oxide form. So the total spectrum itself is already giving us the type of information that we would like to extract on a pixel by pixel basis. Now another way of creating a more detailed analysis of a dataset such as this would be to use some of the predefined color patterns that allow spectra to be gathered from pixels from specific zones within an image. And if we press the define image using zones when we have no zones actually defined, then a pattern will be presented, and this is a standard pattern of squares. There are 16 squares, different colors, and these match with pixels within this image, in fact within all of these images. And when we do the same operation now where we say sum spectra using colors, each one of these boxes produces a spectrum, so there'll be 16 spectra. So now we see spectra with more noise, and that's because they've been summed from smaller boxes of the main image. and with each different spectrum we see a variation of the chemistry. So there's an example where there's more of the metallic tantalum and slightly less of the oxide, and if we go to a different box position then we will find different proportions of these two forms of tantalum.